We're on topic 14 and we're going to try and show some examples of how to use Desmos on the questions in topic 14. So we start with a generalized equation, y equals minus 5x plus 6. We just put in this equation here, and then we just put the coefficients of a, in this case 1, b equals minus 5 right here, and c is 6. So we put those in. And the reason we do that is because once we set up the generalized equation, then we can just vary a, b, and c. And so we get putting a equal to 1, b equal to minus 5, c equal to 6. We get the graph. And now this is the calculation. This is a calculation right here of the axis of symmetry. It's at 2.5, and you can see that it runs here. We'll run down here. And substituting this back into the ax squared equation instead of x, this is x equals minus b over 2a. And we put it back into ax squared plus bx plus c, and we get the minimum value minus 2.5. So here's the axis of symmetry point right here, the x value and the y value, and that gives us the vertex, and that's plotted right here. 2.5, which is right here, and minus 2.5 on the y-axis. So box 5, axis of symmetry, box 6 is the minimum point, and box 7 is the vertex. So these are calculations. Now, what other kinds of things can we do here? Okay, we can show the actual line for the axis of symmetry right here by, instead of writing minus b over 2a, we write x equals minus b over 2a, and now you can see the line for the axis of symmetry. Right here, if we set this equal to 0, you can see that it gives us the two x-intercepts, 3 and 2, right here, 3 and 2. We can actually calculate the x, one of the intercepts, by putting minus b plus or minus b squared minus 4ac over 2a. That gives us one value of x, and we change this plus to a minus here, and we get the other one. So we get the 3 and the 2. 3 is right here, this point right here on the x-axis, and the 2 is this one right here. So to go over this again, box 8, we get the line for the axis of symmetry. Box 9, we get the two x-intercepts. Box 10, we can actually calculate an x-intercept, and we can calculate a y. Now, I know a lot of these things are calculations are redundant, but it's just to show you there are different ways to calculate things and different ways to obtain things. Now, if we take just the graph itself, we can expand it, and we can click on these points, and you can see here's an x-intercept, here's a y-intercept, here's the vertex right here, and the points are identified if we click on these points in Desmos, and here you have the y-intercept. And of course we can expand the axes if we want to, and possibly I should have expanded the y-axis a little more effectively. And so there are different ways of doing this. You can also find the projection mode, and the line will be bigger and thicker, and the points will be emphasized more. That's it's a personal choice. Just an interesting calculation. If you just look at what's here, forget this is an insertion point, so it's not important. I take one x-intercept, and I add the other x-intercept and divide by 2, a half of it, I should get the value of the axis of symmetry, and that's what I have here. So in one of the boxes of Desmos, I typed this equation, and this answer came out in the bottom. Halfway between the two intercepts is the same as the axis of symmetry value, same value that we got. Now let's go look at some different examples. Just move this up here. And you can see here that we put in x cubed minus 9x, and we put in the factored version of this also. It gives us the same equation. You can click this off and just show this. You can click this off and just show that. So that's one thing, and you can see here you've got an x-intercept at minus 3, 0, 0, 0, and 3, 0. So here you can work backwards. Since the intercepts are minus 3, 0, 3, x plus 3 must equal 0 because this gives you this value. X minus 3 can equal 0, so that gives you that value, and x equals 0. So you put this, this, and this together, and you get that. You get the original equation. So this is working backwards from just knowing what the intercepts are. Now, this one here, you got to be careful here because often on a graph you don't see everything, and you can see this graph. I think it goes up like this and then perfectly curves around and it comes down here. So you won't see this, kind of difficult to see, and you have to blow up the graph or minimize it to see. But first of all, we put this equation in here, and a is 7. That's the coefficient of x cubed. B is 47 right here, and C is minus 14, which is this value here. In this particular case, whether we use this equation or we use this one, it's the same thing. We get the same graph. And here again, one of the points right here is 0.286. Now that's a little hard to realize, but it's 2/7. So from the intercepts, you have x plus 7 equals 0. That's this one here. That would give you x equal to minus 7 right here. You've got x equal to 0 and 7x minus 2 equals 0. X equals 2/7. So if you set this all up into one equation, you get the overall equation here. Now, I'm not saying that you can work this backwards. It's not that easy because of this number here. But what you can do is, we did this actual problem, and we did find the intercepts. And by graphing it, you can actually verify the intercepts. So Desmos is very, very useful. Now here, again, we put this into generalized form. We put the value of A is 1 right here. B is 0 because there's no value for B. C is minus 25. It's the coefficient of this. And D is 144. Now, I'm not saying that you need to put B in there, but you can see that this could be used for any kinds of equations, and then you just need to modify A, B, C, D, and the graph will change. And here again, the graph is looks kind of strange because of the way that the graph comes out. You may not see the connection between all these points, but you can definitely see the intercepts right here. And again, the intercepts are minus 4, minus 3 right here, and 3 and 4, which are over here. So you can set up the overall equation, and it is equal to 0. And so good way of checking the problem or actually doing the problem. Now here we have a more complicated problem, page 72, number 2x. If I put this in, I get an error message. It doesn't like that. if I just put this part in, it will draw the graph and show the intercepts. And you get exactly the same thing right over here. This is an insertion point, so don't worry about it. Sometimes when I do these, I forget to remove that or take it out of the box. So whether you use this or whether you use that, you're going to get this. Now you see the graph appearance is different because I've used projection mode and I've clicked on the points. So you can see the intercepts are minus 1.5, minus 0.5, and 3. And so, which is what you would expect from here. 2x plus 3 equals 0, so x equals minus 1.5, that's that one. 2x plus 1 equals 0, x equals minus 0.5, that's that one. And x minus 3 equals 0, and that gives you that one. Now, here's the beauty of Desmos, the sum of 3 squares, consecutive integers, 110. Now, albeit that you could always do this in your head, because obviously the numbers must be somewhere between 1 and 10, and they have to probably be right in the middle. This is not too surprising that the numbers are 5, 6, 7. But here I put the basic equation in, and here it calculated the answer for me. If I start with 5, then 5 plus 1 is the next consecutive, and 5 plus 2 is the next one, so I get that. If I start with minus 7 and add 1, I get minus 6. And if I add another 1 to that, I get minus 5. So you can see no work at all. Can check that right away. Here we have an area problem, and we know that this times this equals 80. So I put that into Desmos right here. It gives me the solution 8 or 10. So this is 8, and this is 18 minus 8 or 10. So if I put 10 in here, I get 18 minus 10, and I get 8. So any which way, it's 8 times 10. And you can see here's the graph of the intercept verifying what we did. So this one is the equation. You can see here, you always know there's an equation if this is here, a graph. This is the graph. It shows the line. This is a calculation. There's no box showing there, so you know that this is a calculation. So you can do it graphically. This gives you the answer graphically, or you can do it by calculation. Now, here's something that's quite neat. Find the dimensions of a rectangle whose parameter is 52 and whose area is 160. We let x equal the width and y equal the length. X times y equals the area. So the length times the width equals the area, which is 160. Then I put an equation in 2x plus 2y equals 52 for the perimeter, because the perimeter is twice the length plus twice the width. Now I got a graph here, and I got a graph here. Which is which? Well, obviously this one here is the linear one. So there's only one that's linear, and the xy equals 160 is this one. And you can see, look what happens. You can show that the 2 points of intersection are 10 and 16. No calculation or anything. You just show it off the graph. So the area is 10 times 16, which is 160. If you take 2 times 10, you get 20. You take and add 2 times 16, you get 32, and you get 52. Now, in previous cases, what we did is we substituted for y in this equation. I solved this, let's say, for x or y and substituted in there. So I only had one variable. You see, the beauty of this is I can use 2 variables, x, y, and here 2 variables. I graph each independently. The point of intersection, this point, lies on this line right here. But it also lies on that line, which means it's common to both. And that's how I know it's the solution. So that completes our discussion on topic 14, and I think some very useful applications.